Alright, this is your Quiz 5 study guide for your upcoming quiz on Wednesday. And I'm just going to be doing these top 7. Alright, so for the first one, let's kind of just take a look at the sigma notation. So we know that this bottom one is where we start, and the top one is where we end. And you also should know that sigma, or this kind of sign here, means sum or adding. Alright, so if we're starting at 0 and ending at 4, we are adding up all the terms in between 0 and 4. So that means we're using 0, 1, 2, 3, and 4. For each of these terms, we need to plug it into this function and then add all of those together. We're not going to find the sum of all of them, we're just going to rewrite them as a sum. So let's start with n equals 0. If we plug 0 into our function, we get 2 to the negative 0. For n equals 1, we're going to do 2 to the negative 1. And I'm adding everything because that is what sigma tells us to do. For n equals 2, we got 2 to the negative 2. For n equals 3, we got 2 to the negative 3. And for n equals 4, we have 2 to the negative 4. Alright, and let's kind of simplify this, maybe just take it out of parentheses. We have negative 0 is not a number, it's just 0. So we have 2 to the 0 plus 2 to the negative 1 plus 2 to the negative 2 plus 2 to the negative 3 plus 2 to the negative 4. Now you can leave your answer as this, but you can actually simplify it even more. 2 to the 0 is 1. And then we're going to add our next term. 2 to the negative 1 is the same as 1 over 2 to the first. Third term is 2 to the negative 2. That's 1 over 2 squared. Basically, we're just flipping it into the denominator and making the exponent positive. 2 to the negative 3 is the same as 2 to the third. And 2 to the negative 4 is the same as 1 over 2 to the fourth. And then we can even simplify that one last time. So we can do 1 plus 1 over 2 to the first is 1 over 2. 1 over 2 squared is 1/4. 1 over 2 to the third, or 2 cubed, is 8. That's 2 times 2 times 2. And then finally, 1 over 2 to the fourth is 16. That's 2 times 2 times 2 times 2. And this would be our final answer for rewriting it as a sum. The next one, same thing, just a little bit more complicated of a function. We're starting with x equals 2 and ending with x equals 5. So that means we're plugging in the terms 2, 3, 4, and 5. Alright, let's start off with 2. Plugging in 2 for every x value. We got 2 squared on the numerator and 2 plus 1 for the denominator. Add. And then we're going to plug in 3. 3 squared, 3 squared over 3 plus 1 for x equals 4. 4 squared over 4 plus 1. And for 5 squared over 5 plus 1. And then, again, we're just going to simplify this just to put it into more readable terms. 2 squared is 4. 2 plus 1 is 3. So we got 4/3 as our first term. For our second term, we got 3 squared on the numerator. That's 9. Over 3 plus 1 is 4. For x equals 4, we got 16 in the numerator and 5 in the denominator. And then for x equals 5, we got 25 in the numerator and 6 in the denominator. And this would be our rewritten sum. Alright, for number 3, same thing. We got our start and our finish. Different functions, so let's write this out. We're starting at -2 this time. And that means between -2 and 3, we got -2, -1, 0, 1, 2, and 3. A little bit more here. So let's start off with -2. Plugging that in for k, we got -2 times -2 plus 3. For -1, we got -1 times -1 plus 3. Now we got 0, 0 times 0 plus 3. We got 1. Keep doing that. 1 times 1 plus 3. Might need to just shove this in the second line. I'm just going to put it right here. K equals 2. We got 2 times 2 plus 3. And for 3, we got 3 times 3 plus 3. Alright, let's simplify this. We got, I'm going to keep it in terms of colors, so we do this one step at a time, which will reduce less errors. -2 times -2 plus 3 is 1. We got -1 times -1 plus 3 is 2. Plus 0 times 0 plus 3 is 3. 1 times 1 plus 3 is 4. 2 times 2 plus 3 is 5. And our last one is 3 times 3 plus 3 is 6. Alright, now we'll put this in the simplest forms. We got -2 times 1, -2. We got -1 times 2 is -1. I'll put that in -2, sorry. Put that in parentheses so we know it's negative. Or you can switch that into a subtraction sign. Plus 0 times 3 is 0. Plus 1 times 4 is 4. Plus 2 times 5 is 10. Plus 3 times 6 is 18. So you can keep it like that, or you can even switch that into a subtraction sign if you wish to do so. I'm going to circle both these answers though, because both are correct. Alright, so for the next 4, they want us to evaluate the summation, which means find the sum of what we were kind of setting up. So it's the same beginning process. We still need to find our start and where we're finishing and finding out like what terms we are plugging in and what we're adding. So we're going to be using n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. Same process as the first 3. We are just going to plug in each n value and set up our sum. So for n equals 1, we got 1 minus 3 over 1 squared plus 1. For n equals 2, we got 2 minus 3 over 2 squared plus 1. For n equals 3, we got 3 minus 3 over 3 squared plus 1. For n equals 4, we got 4 minus 3 over 4 squared plus 1. And for n equals 5, 5 minus 3 over 5 squared plus 1. Okay, so we can simplify these without a calculator. It's pretty basic math. So for n equals 1, we got 1 minus 3 on the numerator is negative 2 over 1 squared is 1 plus 1 is 2. Then we got 2 minus 3 is negative 1, and 2 squared is 4 plus 1 is 5. 3 minus 3 is 0 over 3 squared is 9 plus 1 is 10. 4 minus 3 is 1 over 4 squared is 16 plus 1 is 17. And 5 minus 3 is 2 over 5 squared is 25 plus 1 is 26. Alright, so we can kind of simplify this a little bit more too. We know that negative 2 over 2 is negative 1. This is fully simplified. I changed this into subtraction because we're adding a negative. 0 over 10, 0 over any number is 0. So I'm not even going to write that one down. This one is fully simplified, and our last term we can actually divide by 2 because they're both divisible by 2. 2 divided by 2 is 1, and 26 divided by 2 is 13. Alright, so here's our sum, and then to solve it we can use a calculator. So we're going to do negative 1 minus 1/5 plus 1/17 plus 1/13 equals negative 1. I'm going to round to 3 decimal places, so negative 1.064. If you were to round to 2, negative 1.06. Awesome. Alright, let's repeat the same process. We got our start, our finish, so we're going to be plugging in negative 1, 0, 1, and 2. For x equals negative 1, we have negative 1, put those in parentheses, squared plus 4 times negative 1 minus 1. Make these a little bit bolder. For x equals 0, we got 0 squared plus 4 times 0 minus 1. For x equals 1, I have 1 squared plus 4 times 1 minus 1. And then for our final term, x equals 2, I'm going to put it down here. We have 2 squared plus 4 times 2 minus 1. Alright, so let's simplify these a little bit. We can also, don't really need a calculator for that. You can, but it is kind of basic math. So negative 1 squared is negative 1 times negative 1. That is positive 1. 4 times negative 1 is negative 4 minus 1. I'm going to simplify that even more to 1 minus 4 minus 1. 1 minus 4 is negative 3, minus 1 is negative 4. So there's our first term. Second one. 0 squared is 0. 4 times 0 is 0, minus 1. So we got 0 plus 0 minus 1 is negative 1. There's our second term. Our third term is 1 squared, which is 1, plus 4 times 1 is 4, minus 1. 1 plus 4 is 5, minus 1 is 4. That's a positive 4. And then our final one, 2 squared is 4, 4 times 2 is 8, minus 1. 4 plus 8 is 12, minus 1 is 11. Positive 11. Awesome. And then we can add these up. Don't really need a calculator for this. 4's cancel. 11 minus 1 is 10. And there's your final answer. Alright, same thing for this one. I'm going to go straight into it and say we have 6, 7, 8, 9, 10, and 11. Alright, let's start. For k equals 6, we have 6 plus 1 over 2. For k equals 7, 7 plus 1 over 2. K equals 8, 8 plus 1 over 2. K equals 9, 9 plus 1 over 2. K equals 10 is 10 plus 1 over 2. And k equals 11, 11 plus 1 over 2. Alright, simplify these. We got 7 over 2 plus 8 over 2 plus 9 over 2 plus 10 over 2 plus 11 over 2 plus 12 over 2. Okay, so to solve this, you can use a calculator, but if we notice, all of these values have the same denominator, which means that we can actually add this by ourselves. And we know that our denominator would equal 2. We just have to add all of our numerators together. And so I'm just going to use a calculator to add the numerators together. I'm going to do 7 plus 8 plus 9 plus 10 plus 11 plus 12, and I get 57 with a denominator of 2. There's our final answer. Alright, so for the third evaluation problem, I'm going to jump right in and know that the x values I need to plug in are negative 1, 0, 1, 2, and 3. So let's write these out. We got 3 to the negative 1 plus 1, 3 to the 0 plus 1, 3 to the first plus 1, 3 squared plus 1, and 3 cubed plus 1. Alright, so we can simplify this a little before plugging it into our calculator if we need to. 3 to the negative first is 1 over 3 to the first plus 1. Anything to the 0 power is 1, so that means 3 to the 0 is 1 plus 1. Anything to the first value is the base's value, so 3 to the first is 3 plus 1. 3 squared is 9 plus 1, and 3 cubed is 3 times 3 is 9, times 3 is 27 plus 1. And we'll simplify this a little more. I'm going to keep this one like this and just wait to plug it into my calculator. 1 plus 1 is 2. 3 plus 1 is 4. 9 plus 1 is 10. 27 plus 1 is 28. Alright, and I'm going to plug this into my calculator. 1/3 plus 1 plus 2 plus 4 plus 10 plus 28. I get 45.3 repeating. 0.3 repeating, we know just means 1/3. So 45 and 1/3, if you wanted an improper fraction, this would come out to 136/3. So, whatever form, that is the correct answer.
So for this last section of the study guide, instead of taking a summation, inputting values, and summing them together, we are going to take a sum and represent it in shorthand using summation notation. So to write a long sum in sigma notation, we need three things. We need to identify the first input, which is oftentimes 1 when we find an arithmetic or geometric pattern, but it doesn't have to be. We need the function, which the function is the equation that represents the pattern we see. And then lastly, we need our last input. If you can find those three things, you can write a summation or a sum as a summation in sigma notation. So for this first one, we've got 4 plus 9 plus 16 plus 25 plus 36 plus 49. Okay, now I can tell that this is not an arithmetic sequence, right? It's very clear that, here I'm adding 5, here I'm adding 9, 11, right, 13. I am not adding a common amount each time. So that cannot be what we're doing here, right? I also can tell it's not geometric because, what do I multiply 4 by to get to 9? That's different than what I multiply 25 to get 36. So we don't have a geometric or arithmetic pattern. So we need to look for a different type of pattern. And the pattern I notice here is that these are perfect squares. So when you can recognize a pattern like that, what you want to do is rewrite all of the terms so they fit within the pattern. So instead of 4, I'm going to write it as 2 squared. Instead of 9, I'm going to write it as 3 squared. Instead of 16, I'm going to write it as 4 squared. Instead of 25, 5 squared. Instead of 36, 6 squared. And instead of 49, 7 squared. Because then this allows me to see what is changing and what is staying constant. So we should notice that what stays common is the 2, right? All of these are being squared. So that is going to be part of my function when I draw my summation, right? It's something being squared. And notice that what's being squared is just going up by 1, right? There could be a pattern to it bigger than that, an arithmetic and even geometric pattern, but the pattern is that it's just going up by 1. And we know that our first input to our last input, when we're calculating those things, they also go up by 1. So we can use that to our advantage here. So our function, here's our sigma, our function is just going to be squaring, right? That stays constant, and then what's being squared is going up by 1. So I'll use the variable x, okay, which means that, I'm going to go from x equals something to something else. There's a lot of options here. There's infinite options here, but I'm going to use the one that's most obvious to me. If I'm counting up by 1, if my first input is 2, then I would input 3, then I would input 4, then 5, then 6, then 7. So my last input would be 7. So from 2 to 7, inputting into x squared would give me this sum. Okay. We could start with 1. If you're someone that loves to always start with 1, it's still a squaring function, right? But in order to get 2, it would have to be 1 plus 1 squared. In order to get 3, it'd have to be 1 plus 2 squared. In order to get 4, 2 plus 2 squared. Well, that would work, but then you're not keeping something constant, right? We need one thing going up in increments of 1 and the other thing staying constant. So we would have to put 1 plus x here, x equals 1, to x equals 6, because 6 plus 1 squared is 7. Okay, there are even more ways than just this that you could write it, but these are the two most straightforward ones, and I would say for sure going from 2 to 7 of x squared is the most straightforward one, right? We have our pattern, and our pattern tells us it's perfect squares, so our function is going to be squaring. Then you can just clearly see, oh, I'm going up in increments of 1 from 2 to 7. So there we go. If we take a look at this second one, there's actually two fairly straightforward ways to do this one. The first one I'm going to do is the one that stands out to me, but that may be because I have more familiarity with summation notation. So what I noticed first is I noticed that the 3 stays the same, right? In the last one, we saw that the squaring part stayed the same. So the squaring was part of the function, right? So for this one, since the 3 stays the same, the 3 can just be part of our function, right? No matter what we're inputting, the 3 is going to be in the numerator. So we can just make our function have a 3 in the numerator. And then I'm just looking at a pattern from 5, 10, 20, 40, 80. I can see that that's multiplying by 2, right? Times 2 each time. So I can use my geometric explicit formula to say, oh, the formula for the denominator is going to be a1 times r, which is 2 to the n minus 1. That will go in the denominator because the denominator is following that geometric pattern, right? Whenever I use this geometric and arithmetic pattern, I can always start with n equals 1. And then what's nice here, because I have a finite amount of terms I can see, I'll go n equals 1, n equals 2, n equals 3, n equals 4, and I can see that when my input is 5, my output will be 3/80, right? So I'll end on 5. You could also solve for that because my last input should give me my last output, right? Whatever I plug in for my last input up here should give me 30 over 80 or 3 over 80. So I can also set up an equation and say, okay, I've got the 3, but I just need the 80. So 80 equals 5 times 2 to the n minus 1, and just solve that using any of our strategies from Learning Target 3 of Unit 1, right? Make the bases the same. You've got your answer. But again, we can just count this one. We don't actually have to solve that because we can just see from counting, okay? That's one way you could do this. Another way you could do this problem is I could look at it and see it as a geometric pattern, right? I could go 3/5 to 3/10 to 3/20, 3/40, 3/80, and see, okay, yes, the numerator is staying the same. So that means we're multiplying the numerator by 1, right? The numerator is being multiplied by 1, but the denominator is doubling. So I could think of my common ratio as 1/2 and then just write an entire function for this sequence, right? And say, okay, my n is going to equal 1. A1 is 3/5. Remember, again, we are filling in this formula because this is the formula for a geometric sequence. So A1, the first term, is 3/5. My common ratio is 1/2 to the n minus 1. And then again, I can see I have 5 terms. Remember, the last input is not always the number of terms, but when you start with n equals 1, it does end up being the number of terms. These are the exact same thing. Both would give you full credit so long as you show some sort of thought process. This one is a little bit different, number 3, because there is an obvious pattern, but we have this ... that doesn't just allow us to count how many terms there are, right? Figure out what our last input is by counting. But let's start with what we can figure out. So I noticed that this is arithmetic, right? Remember, when you're looking for the pattern, you kind of ignore the pluses and minuses, if there are minuses, and you just look at the sequence, right? Because all of these are going to be added at the end of the day. That doesn't make some arithmetic and some geometric. It depends on the sequence. This sequence, however, is an arithmetic sequence, right? We can see that we are adding 4 each time, okay? If this is something you are struggling with, identifying the pattern, I would go back and watch my videos from Learning Target 1 because that's really where this was covered. So we have that this is an arithmetic sequence. We know our explicit formula for an arithmetic sequence looks like this: an equals a1 plus d times n minus 1. We can very quickly fill that in and say, okay, the nth term, a1 is 6 plus 4 times n minus 1. So we are about done, honestly, with our summation notation, right? Let's write out what we have. We've got our n equals 1. Again, you can just always start with n equals 1 when it's an arithmetic or geometric sequence, because n equals 1 is what's going to make this formula work. Because when we did arithmetic and geometric sequences, we always started with a1, where n is 1. So I'll put this here. Okay, then the only thing I'm missing is my last input, right? I don't know what my last input is. I do, however, know that whatever it is, whatever my last input is, better give me an output of 42, right? Like in the first one, the last input of 7 gave us the output of 42. Your last input should give you your last output, just like your first input. The first number you plug in should give you the first number of your sum. So I can solve that. I can say, okay, I want 42 to equal 6 plus 4 times question mark minus 1. I just don't know what that is. But lucky for us, that's a linear equation, and we can solve that. Okay, I'll subtract 6 from both sides. I'll get 36 equals 4 times n minus 1. I'll divide both sides by 4. I'll get 9 equals n minus 1. Oops, I'll get 9 equals n minus 1. I'll add 1 to both sides, and I will get 10 equals n, which means that my last input is 10, right? That means n equals 10 gives me 42. 42 is the 10th term of this sequence, so my summation is done here. Surprise, surprise, for this one there's also 2 ways I'm going to show you how to do it. The first way is just the way, honestly, I would suggest most of you do it, especially if you're struggling with this idea, because if we can find a geometric or arithmetic pattern, we can always use what we know from Learning Target 1 to help us fill in the summation. So for this one, I'm going to just write it as a sequence: 4, 16, 64, 256, and I'm going to see that there's a pattern. There's a clear pattern where I am multiplying by 4. Right? That makes this a geometric sequence, right? And if I use my formula for geometric sequences, I have A1 is 4, R is 4, so I'll have 4 times 4 to the n minus 1. That means that I'm going to start with n equals 1, because that is always what I start with when I have a geometric or arithmetic pattern. Then I'm going to put my explicit formula. Then I'm going to see, okay, 4 is when n equals 1, then n equals 2 gives me 16, n equals 3 gives me 64, n equals 4 gives me 256. Again, I could solve for that like we did on the last one, right? I could say, okay, my last input, whatever it may be, has to give me my last output, right? So this equation has to be true. I could divide by 4, use strategy 3 from Learning Target 3, but I don't actually need to do that just because I can see everything that's going on here. Okay, so this is the first way I could write this. Just use the fact that this sequence has a geometric pattern. I know the explicit formula for geometric sequences. The other way I could do this problem is by noticing that these are powers of 4, right? If I can do what I did in the first one and rewrite these and notice what stays the same and what changes, I can write a summation using that. So instead of it being 4, 16, 64, 256, I'm going to rewrite this as 4 to the first power plus 4 squared plus 4 cubed plus 4 to the fourth. And then when I fill in my summation notation, remember, whatever stays constant is part of your function. So notice these all have a base of 4. So I'm going to put a base of 4. And what's changing is my variable, or my exponent, sorry. My exponent is going 1, 2, 3, 4. So again, I can see if my first input is 1, I'd get 4 to the first, then 4 to the second, then 4 to the third, and then lastly 4 to the fourth. So this is another way you can look at this one. This way is a little faster and looks a little cleaner and nicer, but it doesn't use what we know about geometric sequences. So that's why I was kind of saying, if you're struggling with these, you can rely on the fact that it's going to be arithmetic or geometric and always use those explicit formulas. But I don't want to lead you guys down the path and think that's the only way that these can be done. And then that is your study guide. This study guide will both prepare you for the quiz on Wednesday that covers this content, but also for the content you may see on the midterm over this topic. If you have any questions about anything that we covered here, send me an email.